Hi everybody, in this recording we will be going over section 3.8, Newton's method. Our main goal is that after you watch this video, you will be able to approximate a zero of a function using Newton's method. Newton's method is an approximation technique that uses tangent lines to approximate the real zeros of a function, also known as the function's x-intercepts. So we'll follow these steps of Newton's method for approximating the zeros of a function. So we let f evaluated at c be equal to 0, where f is differentiable on an open interval containing the point c. Our first step is to make an initial estimate of x1 that is close to c, and we can sketch a graph if possible. Our next step is to determine a new approximation, xn plus 1. This will be equal to the previous approximation, xn, minus the function evaluated at xn, so f of xn, divided by the first derivative evaluated at xn, so f prime of xn. The next guideline, or the next step, is that when the absolute value of xn minus xn plus 1 is within the desired accuracy, we let xn plus 1 serve as the final approximation. Otherwise, we will return to step 2 and calculate a new approximation. So each successive application of this procedure is known as an iteration. Now here's an example of using Newton's method to approximate the zeros of the function f of x is equal to x to the power of 4 minus x minus 3. So we will continue the iterations until two successive approximations differ less than 0.0001. So first we can begin by sketching the graph of f, and we see that the function has two zeros, one near x is equal to negative 1.2 and one near x is equal to 1.5. So first we will differentiate f to obtain f prime of x, which is equal to 4x cubed minus 1. So next we will form the iterative formula, so the one that was defined in the previous slide, where we said xn plus 1 is equal to xn minus f of xn divided by f prime of xn. So we will have xn minus, now our original function, but we are evaluating it at xn, so we just plug in xn every time we have an x, divided by our first derivative evaluated at xn, so our first derivative, just plugging in xn whenever we have x. So our first approximation, we chose x is equal to negative 1.2. So x1 for our first iteration is negative 1.2. Evaluating the function at that value, we get 0.2736. Evaluating our first derivative at negative 1.2, we get negative 7.912. And then dividing this value by this value, we get negative 0.03458. Now subtracting this value from our first xn, negative 1.2, we get negative 1.16542. So this will now be our x2, our next approximation, right here. And then we will evaluate the function at that value, and this is what we get. And then once again, evaluating the first derivative at this value, dividing these two and subtracting them from the xn, we get our x3. Sorry, from our x2, now we get our x3. And we repeat the process. So now this is our new x3, negative 1.16403. So we evaluate the function at that value, evaluate our first derivative, divide the function evaluated at that value by the first derivative evaluated at that value, and subtracting it from our xn. Now we get this new x4, but we see that they are approximately the same. So because the final two approximations for each zero differ by less than 0.0001, just like the instructions told us, we can estimate that the zero of the graph at the left-hand side, right here, is approximately negative 1.16403. Now to find the other x value, or the other x-intercept, the one that we stated was an x near x is equal to 1.5, we can repeat the process, but now our x1 will be 1.5. Now here's an example in which Newton's method fails. So we have the function f of x, which is equal to x to the power of 1 over 5. And it is not differentiable at x is equal to 0. So we need to show that Newton's method will fail to converge using our first approximation x1 equal to 0.1. So first we take the first derivative of f of x, and that is equal to 1 over 5 times x to the power of negative 4 over 5. Then the iterative formula will be xn minus the function evaluated at xn, so our original function, just plugging in xn right here in the numerator, and then divided by our first derivative evaluated at xn. So our first derivative, just plugging in xn right there. So upon simplifying we get xn plus 1 is equal to negative 4 times xn. So our first approximation, we stated it was 0.1, so plugging that in, and our function evaluated at that value is 0.63096. Our first derivative evaluated at that value is 3.15479. Now dividing this value by our first derivative evaluated at 0.1, we get 0.2. Now subtracting 0.1 minus 0.2, we get negative 0.1. So that'll be our x2, or our new approximation. So now we will evaluate the original function at negative 0.1. We will evaluate the first derivative at negative 0.1, and we will divide these two values. And we get negative 0.2. And negative 0.1 minus negative 0.2 yields 0.1. So now we're back at step 1 right here. So x3 is equal to 0.1. So we get the same values that we got for our first iteration here. And then the pattern will just repeat itself. So this table and graph indicate that xn continues to increase in magnitude as n approaches infinity. And so the limit of the sequence does not exist.